Alrighty guys, what's up? BenchDaddi here today, and I'm super excited for this video because this has been a long time in the making. I know I haven't posted anything or made any videos in a while, and it's been a lot of life changes in the last couple of months. I've been traveling most of it, and now I'm out in Seattle for an internship this summer. So I'm gonna try to start making some videos as I can. But this is one I've been working on for a while, and I've been really trying to get out because I think it's super important and it's something that really, to my knowledge, isn't really available. So the subject today is going to be GPU benchmarking, and this is super important, at least in my mind, because GPUs are incredibly expensive, and if you don't know what you need, you might end up overpaying or buying something that's underpowered. Um, so I think GPU benchmarking is really important, and there's not really, to my knowledge, like I said, a open source benchmarking suite. So that's been my goal, is to make really a open source benchmarking suite, basically for um, AI, ML, and DL. So that's what this is, and I'm just going to walk through it, briefly, the README, and kind of tell you what it is. So that way, in case you're interested, you can watch the next part of the video, which will be going through a little bit of the code. And then in a subsequent video, I'll actually compare all the GPUs that I have. So basically, or at least the ones that I like. So the P40, P100, and the RTX 3090. So, part of this, what took me so long, is to sit down and really think about what would make the most sense as far as metrics, as far as GPU, or sorry, uh, DL architectures to try. So what I eventually came to is um, I started with three. So three models representing three of the major GPU architectures. So basically transformers, and if you've done anything in transformers, have there's no way that you haven't heard of BERT. And then from RNNs, there's the LSTM, and then CNNs, of course, is ResNet 50, and that's what I do a lot of work with. So um, anyway, I figured that these three architectures, and then the kind of quintessential models that go along with them, would be a good place to start as far as creating a benchmark. So basically what I did is um, built a training and test script for those particular architectures, or those models within those architectures, and then found some publicly available data sets, at least one, at least at this moment, per model. And eventually, the goal will be to expand to multiple data sets, and then you guys can choose how you want to configure things. But basically, so that was you know the models that we're going to use, or the models I think are important to use. And of course, we'll expand those out in subsequent versions. I'd like to include like large, or the open source LLMs, and diffusion, and all these other things. But just for a start, to get a baseline and to get the kind of core, I think these three models are good to start with. And then the next problem was, okay, how do we actually evaluate this? And I think there are a couple of things that are really important when you're looking at evaluating GPUs. And then the first and probably most important, in my opinion, is throughput, and then execution time. So basically, how long does it actually take per epoch or per batch, or whatever you want to kind of assign. And I look at each of those in this benchmark. And then for me, another important one is data transfer time. So you have PCI 3, 4, 5, you have NVLink, you have all these different things that offer different data transfer speeds. So to me, I think it's worth understanding how much of your time, your training time or inference time or whatever it is going, your actual overall execution time, is going to data transfer. So that's an important piece for me. It can help you identify bottlenecks, and so on and so forth. Um, and then memory usage. So this is also really important. Um, you need to understand um, how a particular model is utilizing memory, and how much memory your GPU has, how much of it's actually being allocated towards the model itself, and then towards the tensors surrounding it. Um, and all the other things. And then there's also there's also overhead um, for the GPU to kind of run all those things. So understanding the way that the memory is managed is also important. So but anyway, the repository structure is pretty simple. Um, there's at this point there is a file. So there's one for BERT, one for the LSTM, and then one for the ResNet, and these are basically self-contained, and they have an accompanying config file. So there's a couple config files in here. So there's BERT, one for the LSTM, and one for the ResNet, and then as many things as you can configure. I tried to allow you to configure as many things as I thought were reasonably possible. Um, but if we go back to the README, um, all of those individual, well, this will ever load. There we go. So all of these are run by the main program, RunPy. So this is basically just going to go through and run each of these, and then the data and benchmark information is going to be output in the logs folder. So there's going to be a data folder and a log folder that are created, and all the data that's required to run these models we put there. I also realized that I forgot to go over, or I forgot to link the data sets and also go over them. So while we're kind of on the topic of data, I'm going to go ahead and interject and go over the data sets really quick. So for BERT, we're going to be using, or we used Hugging Face's IMDb dataset. So basically, um, it's pretty well known, but it's movie reviews labeled as basically positive and negative. So highly polar movie reviews. 25,000 for training and 25,000 for testing. So that's a pretty good, um, not too large data set and a pretty standard task. So I felt like that was a pretty good choice as far as a data set for BERT to do some text classification. And then similarly with the LSTM, I wanted enough data that would be relatively substantial, but not so much that it would take tons and tons of time to train. So I went with UCI's publicly available um, individual household electric power consumption data. So that's about 2 million features, or sorry, 2 million instances, 9 features. Um, and they are basically time series predicting, or using this time series data to predict um, global active power. So that's the goal there with that particular data set. And finally for ooh, back and then finally for image classification, we're gonna use we did use the CFAR10 data set, and that's also pretty standard as well for um, image classification tasks. So if we go here and then we go to there we go CFAR10. This is basically subsets of a larger um, 80 million small 32 by 32 images. So this was actually 60,000 32 by 32 images with 10 classes. And I guess it's airplane, automobile, bird, cat, deer, blah, 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 blah. So anyway, that's what we're using. And then it's a basic image classification task with this ResNet 50 here. So just wanted to highlight those before we move on. I also included this other script I thought was pretty useful. This is basically a GPU max loading script, so you can um, pretty much set GPUs by their ID, and then it will put a max load on them, and then you can basically use that to see if they're overheating, or um, if you have enough coolant, or not enough coolant, but if you have a good enough cooling system for them, whether they're overheating, whether they're thermal throttling. And then also you can test the server noise, or I guess workstation noise if you have that, to see what it would be like running at max load for extended periods of time. And then finally, guys, there's a list of requirements so you can set up your virtual environment. And then if you use Conda, which highly recommend. To use Conda, you can just run the script, and it will go ahead and set you up in a virtual environment through Conda, and you can easily um, run the scripts that way. So that's the kind of main overview of all the files. Um, Python 3.8 or higher. I use 3.10, so I'd recommend that. You need to have CUDA drivers installed. And this is just going to go over like kind of what I said, how to actually pull everything down, install it. This goes over all the configurations. So one thing I want to highlight here is that by default, a lot of models are going to use floating point 32 or a single precision. If you want to use mixed precision, I've enabled a flag so that you can test these on mixed precision. So that's going to be particularly important, and I'll show this in a subsequent video, but this is going to be particularly important if you're using like Tesla GPUs, like particularly like the V100, A100, anything like that that has really high half precision that's kind of made for this kind of thing. Um, Enabling this is going to be important to actually see what the true performance or what you could get with mixed precision, because it should in theory be significantly higher than what you would be getting just kind of constraining it to only using FP32 or single precision. So that's one thing I wanted to highlight. And we'll kind of go over some of these generic ones. So batch logging, this just specifies it's going to output or basically update you on how the model's performing every 100 batches. Um, and if we look at the example log, that'll make a bit more sense. So let's look at this one. But if you see, like, it says epoch 1 batch 100 out of 391. So basically, it's just going to give you the loss, transfer time, and then execution time every so often um, as it's going through the training process. So let's go back to the README. So other things, the GPUs, you can set as many as you want. If you have 8, you can set all 8, and it will use DDP, distributed data parallel. And then, so basically what it's going to do is it's going to, uh, each GPU, and this can also be across machines as well, but each GPU will communicate via this local host. In our case, it's just going to be one machine because it's set to local host, but you could change this if you wanted. Um, and anyway, they're going to communicate over this port, and they're going to exchange information back and forth with each other. So you can scale this out to as many GPUs as you can fit on one machine, or you can just use one, whatever you want here. But just you got to put the GPU IDs here in a list, and then if you want to use CPU, you can set this as -1. And again, there's the use mixed precision flag. I've set default to 3 epochs. So if you want more epochs, you can, but I think 3 is plenty to, the 3 is plenty for benchmarking. I don't want this to be running for hours while it's just doing nothing but benchmarking. I set the learning rates and all the hyperparameters is what I thought was fairly normal, or I guess kind of standard for these. Seemed to work well anyway. Same thing with the data sets and data loader related stuff. So this is just the max sequence length, um, batch size. In this case, since we're doing sentiment classification or text classification, there's just only 2, positive and negative in this case. So that's the number of labels and the number of workers. How many basically workers do you want for the data loader? A lot of the same stuff here for the LSTM. You can also adjust like the hidden layer size, input size if you want to use a different data set. So, all these things are configurable. Sequence length, basically how far back do you want it to actually look? So this is time series, this is text classification, and this is going to be image classification for ResNet. So I tried to hit a lot of the major, or give you some different data types, um, some different modalities: image, text, time series data. So this way, I was trying to make the benchmark as well rounded as possible for just three models. I know it's a bit sparse still; it really needs a lot more, but this is quite time consuming, and at least this way will give us, myself and the community, you guys, a place to start. Okay, so yeah, all this is pretty standard, and then I guess this is going to tell you just how you can run a single, um, basically run a single benchmark, or you can run all of them with the main script. You can also, run the max loading if you want to check the thermals or noise or whatever. And then this goes over the actual evaluation metrics themselves, in a bit more detail. So tells you that by default you're going to be using single precision with 3 epochs. Memory allocate. It's going to look at memory allocated and memory reserved. So basically, memory allocated is the model and all the accompanying tensors, and other data structures that may be relevant. Um, and then the reserved is going to be anything that it reserves for additional overhead, or maybe future allocations, or anything like that. So basically, this is what the GPU reserves, and this is what's actually being used in terms of tensors and um, information to hold a model. And then this is basically output as soon as the model's loaded, so you can get an idea of how big the model itself actually is before you're loading any batches. Um, and then it's assessed again every 100 batches, so you can get an idea of what the overhead beyond the model itself is. Okay. Um, Execution time is pretty straightforward. It's just how long it takes to get through a batch, epoch, um, full training or test, and then these are averaged and reported for each GPU per epoch and then per batch, and then also they're globally averaged for training and test. So that's just across all GPUs and across all of epochs. Um, Same thing for data transfer time. So same thing here as far as when they're reported and when they're averaged. Um, but this measures the time it's taken to actually load the data for each particular batch onto the GPU. So, and this is also expressed as a percentage of the total execution time. So basically, like what we're trying to assess here is how much of our time are we actually spending loading data. Um, and the larger the percentage, the probably worse that really is. That should be a very small percentage of the actual time should be spent loading data. Otherwise, that's going to be a good clue that your bottleneck is in data loading, or is in basically I/O, not in model computations. All right, and then finally, throughput. Basically samples. So a sample could be anything from a image in the case of like computer vision, to a like tokenized piece of text for NLP. So basically any singular model input. And the idea here is we want to see how many inputs can the model process per second. And this will be basically summed, or um, this will be calculated for training and test, or inference, training and inference, whatever you want to, however you want to think about it. Um, and then the that's going to be output per model. So basically, or sorry, per training and test. So each model, BERT, ResNet, um, LSTM in this case, they'll all have a training and a test. They will all have a throughput associated with training and test, and then that'll be summed across um, that will be summed across each model. So basically, there will be a score given for ResNet, a score given for BERT, a score given for LSTM, and then finally, as a kind of aggregate score or final benchmark score for the GPU, um, they're going to be all summed. So all of those are going to be summed together to give you an overall benchmark score. So, I don't really love that metric, but it's the most succinct thing I could think of at this point. So that's what we're going to go with for now. I'll probably update it later with something better when I can think about it. But but for now, basically, that's the the overall score given to assess how good or how a GPU compares to its peers is going to be basically the aggregate or the sum of its throughput during training and test for these three um, different models. So that's what I'm going to use to kind of as a yardstick to measure each GPU against some other GPU, where I think is probably the best yardstick at this point. So, so yeah, that's a pretty good summary of all the metrics we're looking at. And then, of course, this is open source under the MIT license. Please, you're more than welcome to contribute. I welcome it. I really would love some people to kind of collaborate with me on this and help me expand it. And then if you want to use it for any academic work or you want to use it in your own thing, all I ask is that you cite in some way you can use this or whatever. But just give credit back so people can find this. I don't really even care so much about the credit. I just want people to be able to find this, um, and then also be able to add to it as well. So we can kind of get the word out and turn this into a kind of a community effort. So, and then of course, guys, please feel free to email me, or you can look in my YouTube bio and you can get with me on Twitter or really any of the other platforms, Discord, and I'll be happy to talk about this or really anything else that's related. So, okay, yeah, that's the good summary. That's all kind of the boring stuff. I'm sorry that started in the beginning of the video, but if you're still here with me, what we're gonna do now is I'm just gonna briefly go through some of the logs. So this is what the logs actually look like. So it's gonna tell you for each GPU. In this case, I use um, two GeForce RTX 3090s. Um, it's going to give you your CUDA version that you're using for both, or it's loaded onto both. It's going to tell you the GPU, so whatever device you selected, and the name, the compute compatibility, the total memory. And this compute compatibility, all this is basically the particular model of your GPU. So basically, some iterations of the same GPU will have basically higher compute capability than others. So this just kind of tells you which exact model it is that you're talking about of a particular GPU. So I didn't know that. I had to look that up as well and thought that was kind of interesting. Um, all right. So as you can see, as we talked about before, every 100 batches or every batch increment, it's actually a variable you can set. It's going to let you know um, about the loss at that particular batch, about what the data transfer time was at that particular batch, and then also the execution time, just to kind of so you can kind of see how things are going as it's training. That's why I left that in there, and I left it variable so that you could adjust it. And then also, it's going to periodically let you know about the memory allocated, memory reserved. So this shouldn't really change that much, really, probably ever. But this, if it does change, it might let you know something weird's happening. Um, and also, this is a bad example. Let's look at. I thought it was a resonant I was looking at. Yeah. So there we go. Um, but if you notice, after it, so this is basically after the model's loaded. So after the model is loaded, the memory required to load the model was only about 0.2 gigabytes, but it reserved more memory um, in case, for overhead and whatever else happens. And then if you notice, once we have the first batch, the memory allocated goes up to 0.49 gigabytes, and the memory reserved goes up as well. So that's basically this minus this is what you're actually allocating for this first batch, and then each subsequent batch. And then this is the memory reserved difference between this and this is all the other space that you're just reserving for any overhead and any overflow or anything else that you might need. So just wanted to explain that a little bit in context here. Um, so again, after every epoch, the information is aggregated for each GPU. So in this case, summed, and it's going to tell you average across all the batches, data transfer time, the average data transfer time. So basically, percent of the time spent executing, how much of that did we spend transferring data? And that's going to tell it to you for both GPUs, or I mean, as many GPUs as you have. So it could be 3, 4, 5, 1, doesn't really matter. And then the same thing again, guys, for Epoch 2, nothing new there. And then Epoch 3, again, similar. So we said we were going to do 3 epochs. And then this is the kind of the global training metrics where it's aggregated across all of those and across the GPUs. So the total training time across those 3 epochs was 110 seconds. The average batch execution time was about 0.05 seconds. Negligible batch transfer. In fact, it was less than 1% of the total execution time that we spent across those first 3 epochs. And then finally, the kind of benchmark yardstick is the global training throughput. So how many samples, in this case, how many images, because it's ResNet, were we able to process in a particular second, or I guess on average. And then finally for testing, how many? Let's see, a lot of the same metrics. This is aggregated across um, the test. So basically, total training time for the test, or sorry, total time needed to kind of run through all the test samples. It was only 100 or 1.7 seconds. The average batch execution time was about 0.02 seconds. And again, throughput, um, and then throughput. Kind of weird that those two had such different throughputs for each GPU, but you know, is what it is. And then finally, um, it just gives you those kind of global metrics across both GPUs for the test side. So test inference, whatever you want to call it. But once the model is trained, using the model to actually um, predict on the unseen samples. So and yeah, so this is the test throughput. So basically, um, that is a summary of one of them, and all of the log formats are the same across the models. I try to keep everything as consistent as possible. And then finally, this is the results. So basically, those scores I was telling you about. So for ResNet, the the score is 4,688 and change. The BERT score is basically this is the summed throughput for ResNet of training and tests, some throughput for BERT training and tests, some throughput for the LSTM model training and tests, and then all of those summed to give us our final benchmark score. So as you can see, there's quite a disparity between BERT, between LSTM, between ResNet, all because there's different modalities, different data sizes, all this other stuff. So I don't love this metric to actually compare, but at this point, I think it's still probably the best benchmark, just adding them all together and seeing who has the best performance across all the models and across training and test. So, and of course, you may disagree. You may have a better idea. I'm totally open to any and all suggestions. So please feel free, like I said, to collaborate with me on this and give me any better ideas. So all right, but now what I want to do is I'm going to pull this down, show you guys how to use it. All right, guys. So I just logged into one of my servers that has some NVIDIA GPUs on it, or in it, I should say. So there we go. That's 5, 2 3090s, 2 P40s, and 2 P100s. So we're going to be testing stuff out on the RTX 3090s today. The first thing we need to do is we need to go over here and we need to copy from the benchmark suite, copy the URI, come back. I'll make this a little bit bigger so you guys can see, but we need to clone the repository. So there we go. It's pretty lightweight. And the next thing we need to do is we need to um, create our environment. So you can either run pip install dash r requirements and install it that way. Um, after you've already created a virtual environment with like Vim or virtual env or something like that. But if you have Conda or you know have any one of the flavors, Anaconda, Miniconda, you can do it this way. And there are steps in the README as far as if you want to install it. But so we're just gonna run. Well, first of all, we need to cd into the GPU benchmark suite, and now we can run Python. Sorry, setup, and that should go through and create a virtual environment for us. And this is going to take a minute. So I'm going to go ahead and pause this, but don't cancel it. It's not frozen. It just takes a little bit because there's a ton of packages. So just bear with it. So I'm going to pause and then I will come back when this is done. All right, guys. So looks like we just successfully created it. So we can just make sure by running conda env list. And there we go. So now we're going to activate this environment we just created. Vim. Okay, cool. So now we're ready to roll. We can run any of these. So you can run any individual tests with the individual model. So BERT, LSTM, ResNet, or you can just run all of them. So we're just going to go ahead and run all. So it's going to be literally as simple as Python run.py. And then there we go. It's going to start downloading all of the data sets. In this case, it's just downloading CFAR10. So if you look, it's downloaded CFAR10 into the data directory. And then it's going to go ahead and um, start creating us these logs. So yeah, there you guys have it. That's pretty much it. It's going to run through all of these as soon as it gets finished downloading the data. And then it's going to eventually output a score for the GPU or GPUs that you selected. Is GPUs 1 and 2, so it's assuming that you have two GPUs. So, and for us, that's going to be GPUs, both of the 3090s. So, anyway, guys, once it's finished, let's go ahead and skip because it's going to take about 30 minutes probably to run all of those. But once it finishes, you're going to get an output that looks almost exactly like this. It's going to show you all the information we've kind of already gone over. And it's going to do that for each of the models. And then it's finally going to output you a score, an aggregated score, so a sum score for the ResNet, the BERT, the LSTM, and then finally give you an overall benchmark score, which you could use to compare to other GPUs. So for example, what you could do is you could compare like you could adjust all of these to 0 and then compare one GPU versus two GPUs and see what kind of a speed up you get. You could run it, like for me, I could switch this to 1 and 2 and run it on, two different sets of GPUs and then compare. And then you could also set it as -1 with the CPU and see how long that takes, and then use that as a benchmark to see how much better you can do than just using CPUs. So all of this I will do in a follow-up video because it's already kind of long, and I just really wanted to kind of introduce the benchmark, go over it, um, and show you guys how to use it. And then in the next video, I'll actually run it on a bunch of different configurations. So I'll compare the CPU to the P40, P100, 3090, and then I'll do for one GPU, two GPUs, and then I'll compare all of those outputs and show you guys how all the GPUs actually stack up against each other. So that'll be coming. I appreciate you guys for bearing with me today, and I hope that you find this useful. And I do also hope that you will collaborate and help me expand this benchmark. If you're interested, would certainly be most appreciative of that. So anyway, guys, thank you very much. And without further ado, I'm gonna let you go. I'll see you in the next one. All right, guys. Brief reminder here. If you enjoyed the content, please consider giving me a like and a subscribe so I can continue to grow and produce better and better content for you. If you really enjoyed the content, you might even consider buying me a coffee, and the link for how to do that will be in the video description below. If nothing else, please just give me some feedback in the comments and let me know how I'm doing, if anything's unclear, or if there are anything that I can improve on. Thank you again, guys, and have a great rest of your day. Bye-bye.